It is my pleasure to introduce Stephen Murdoch from the University of Cambridge, here to talk to us about smart card systems and their security failures. So, if you'll join me in welcoming him to the stage, please.
Okay, good afternoon everyone. Hope you can hear me okay. So this is some work that I've been doing on the security of the chip and pin system in the UK, which I've been doing with two of my colleagues, Ross Anderson and Sarge Rimmer. We're all from the security group at University of Cambridge. So for those of you who don't know of the terminology, the chip and pin system is the UK implementation of the EMV protocol. EMV stands for Europay, MasterCard and Visa, and it's the most widely deployed smart card payment system in the world. It's fully deployed across the UK. It's deployed also throughout most of Europe, a few exceptions, I think, apart from Italy. It's fully deployed. It's the same in Germany. And it's also starting to be rolled out in North America. Not so much continental US, but it has been started to be rolled out in Canada. It applies to both credit and debit card payments. From the perspective of the protocol, it's entirely identical. And the way it appears to the customer is they put their smart card into the point of sale terminal. They are shown the amount that they're going to authorise. They enter their PIN. If the PIN is correct, and this is verified by the card itself, not by connecting to the bank, if the PIN is correct, then the transaction is authorised. So now let's look into a little bit more detail about how this works in the underlying protocol. The actual specification for EMV is huge. It's about 3,000 pages. So this is a very high-level overview. I'm only going to talk about the UK implementation, but the system in Germany is very similar. So firstly, the customer puts their card into a device called the PIN entry device, commonly called a terminal, but this is consisting of a smart card reader and a PIN pad. The card then sends to the PIN entry device the card details, which is the account number, the cardholder name, expiry date, and a whole bunch of other details. It also has a public key certificate that is signed by the bank, which is in turn signed by someone like Visa or MasterCard, to say that this is a real smart card issued by a particular bank to a particular account number. And also, at least in the UK, a copy of the magnetic stripe details is stored. That's because a lot of banking infrastructure is fairly old. It's based on systems that haven't been updated and are very expensive to update. So for backwards compatibility, there's still the possibility of doing the equivalent transaction to a magstripe transaction. And there are two weak points of this protocol, and that's one of them, the copy of the magnetic stripe. And then, once the card has sent all its details, the PIN entry device will send to the card the transaction, so the amount, how much value it's for, also the currency and the type. The type might be, it's going to be a point of sale goods, or it could be cashback, or it could be ATM. And then, if the card is happy, it will ask the customer to enter the PIN. The customer will enter the PIN into the PIN entry device, and that gets sent unencrypted to the card. And that's the second weak point of the protocol. And then finally, the card will check whether the PIN is correct. If the PIN is wrong, it will decrement a counter, and it will only allow a PIN to be verified incorrectly 3 times in a row. But if it's correct, it will return an authorization code to the PED, and the PED will pass that to the bank, and then the transaction is complete. So there's 2 bits of information here that must be kept confidential. There's the magstripe details, and there's the PIN. The reason these need to be kept secret is if someone discovers this information, they can use it to make a fallback transaction. This is that even though smart cards are deployed across Europe, they're not deployed in all places in the world. And if you want to use your card abroad, it still needs to have the mag stripe. So what crooks can do is, if they know your mag stripe and they know your PIN, they can then write this to a blank card and then use this in a country where chip and PIN isn't deployed and take money out of your account. In fact, this even works in some countries where chip and PIN is deployed, like the UK. At least in 2007, it was still possible to clone a chip and PIN card onto a blank card that has a mag stripe and then use that. In other countries, this is supposed to be impossible, but it's very hard to tell what is actually happening inside bank systems, so to be sure, you really have to try it out. So because of these 2 bits of critical information being sent effectively unencrypted, PIN entry devices are required to be tamper-proof, tamper-resistant. And these requirements come from a number of sources. One of them is Visa. They have a certification scheme for PIN entry devices. If they don't pass, it's not possible to use Visa cards in them. Apax is the UK banking industry body, and they also have a scheme that is based on common criteria for certifying various properties of PIN entry devices, but one of these properties is that it's tamper resistant. And a replacement to the Visa scheme is now known as PCI. Those of you who work in retail or banking will have probably heard of the PCI DSS, the Data Security Standard. This is the requirement that you don't store certain details of bank cards, and when you do store them, they're adequately protected. So that's DSS, but there's another standard, PCI PED, which is certifying PIN entry devices, and that has now superseded the Visa scheme. In all cases, an external lab performs the validation. In the case of the Visa one, it was certified. It's a lab that has been approved by Visa. With PCI, it's approved by the PCI Council. With the Apax common criteria, the way common criteria works is that the governments themselves get to choose what labs are certified in that country for doing common criteria evaluations. But the standards are roughly the same in all cases. The PIN should not escape the box. The PIN should send to the card and to nothing else. If it's attempted to be tampered with, then effectively the PIN entry device should self-destruct. And the sort of sums of money we're talking about is the Visa standard requires that it cost more than $25,000 per PIN entry device to tap it in an undetectable way that will allow the PIN to be extracted. So that's what the theory says, but we wanted to find out how well do these mechanisms work in practice. So let's have a look at some of them. This is the Dione terminal, the Dione Extreme, and it has a fairly simple tamper-resistant mechanism. You can see the yellow thing, that's a battery backup. That's how it stores the data in the non-volatile memory. And there's this blue thing on one side and a contact on the other. These keep the connection to the battery closed, but if you open up the case, then the battery is connected and it wipes its keys. The idea is then that the device is useless and has to be sent back to the manufacturer. This is not particularly secure for a number of reasons, one of which is that it's comparatively easy to drill in through the back and then defeat this tamper-resistant measure. All you have to do is short out the contacts so it doesn't work, but at least they're trying. This is the Ingenico terminal, which I'm going to concentrate on in this talk. And this has much more sophisticated tamper-resistant measures. So this thing that is shown in the circle is a micro switch, and it is depressed by a plate on the other side of the casing. And also there's this steel plate over the switch to make it a bit harder to drill through and try to defeat it. That was the back, but on the front you can see that there's these normal contacts that are for the keypad, but also between each of these normal switches there's these 4 extra switches, and these are depressed by the front surface, and these make contact with extra contacts that are put on the circuit board. So if you lift open the front, then it disconnects the battery and deletes the keys and makes the device useless. If you look into a bit more detail, here's the micro switch again, and you can see it's surrounded by a raised circuit board, and there's this labyrinth of PCB traces, and this is a sensor mesh. If you drill through this layer, then this also disconnects the battery. On the circuit board, an entire layer of the multi-layer circuit board is another one of these tamper meshes. So if you drill through the PCB, then you are going to be detected. And also, if you look in the top left of this picture, around that extra switch, there's a extra contact. And what this is intended to predict is that if you want to defeat this switch, one way of doing it is by injecting silver ink, which will close the contact and allow you to take off the face. But there's this extra ring around it, which is also a contact, and if any of the silver ink leaks and connects to that, then that's detected as well. So it's actually pretty hard to bypass this tamper mesh. If you look at it, it's very fine. You need an extremely fine drill to get through there. But notice there's a big hole there. I'll come back to that later. The actual CPU, which both does all the confidential processing and stores the keys, is embedded in something that looks like a cryptographic coprocessor that you'll find in some high-end banking machines. It's potted and then covered in another one of these tamper meshes. If you drill through this, it detects it and deletes the keys. Going back to the diode briefly, it looks significantly different. All that happens here is that the module, which contains both the CPU and the memory and the clock crystal and also the keypad, is potted into epoxy, and we can see that you can fairly easily get through the epoxy. There's no tamper mesh, and you can drill into the CPU if you like, but in fact you don't need to go that far. So, at least in the Ingenico terminal, and to a certain extent the Dione terminal, the tamper resistance measures are quite extravagant. It is going to be quite a challenge to open up the case, although criminals have been able to do this, and even more of a challenge to get into the CPU and extract the keys. But these keys are not all that useful to a fraudster, because all these keys do is protect the communication between the bank and the PIN entry device. They don't protect the customer's PIN or the magstripe details, because these are sent in an unencrypted form. They're sent from the card to the PIN entry device itself. So if a fraudster can somehow circumvent the tamper resistance measures, connect to the almost unprotected I/O lines, and record these details, they can then capture the information, write it onto a blank magstripe. They used to be able to use it in the UK. They might not be able to use it anymore, but they can certainly use it abroad. And what we found is that the I/O lines are almost completely unprotected. It takes little more than a paperclip and some off-the-shelf electronics to connect to these, record the details, and then send them off to a PC. But when we've previously tried to show that there's been weaknesses in the UK banking system, The banks have always responded saying that this is purely theoretical, this won't work in the real world, there are other measures that we can't talk about, but that would definitely prevent the attacks that you're talking. So what we did is demonstrated it for real. We asked the BBC to get us a real chip and PIN terminal and connect it up to a standard merchant account, do some real transactions, and then we record the details. And we filmed the results, and this appeared on BBC Newsnight. So I'll now show a 5 minutes or so video on the results that we found. The full copy of this can be found on, I think, Google Video now, and there's a link to it from my website. Can you turn up the sound? Oh, yes, you're right. Thank you.
Good evening. In a very short space of time, the system of chip and PIN, punching in a code number each time you use your credit or debit card, has become ubiquitous. The great advantage, we were told, was that it had such good security protection. How could anyone steal from us if only we knew the numbers which would make our card function? As Susan Watts reports, it seems we were naive. By the way, while they were filming this piece, our cameraman fell victim to the fraudulent withdrawal of £1,000 from his account by someone in Serbia.
These were once intact pin entry devices, or PEDs, which Stephen and Saar bought on eBay for around £30, giving them free rein to explore the inner workings of each device. This one is made by a company called Ingenico and is among the most common of the PEDs in use in UK stores today, in shops including Boots, Asda and the Co-op Group.
We found ways in which we can get into that interface between the card and the processor, and we're able to read the data as it went back and forth.
It sounds simple enough in theory, but these PEDs aren't live. The real test is whether the attack works on an active terminal. Away from their workbench, we provided the Cambridge duo with a live merchant's machine and a real credit card to test out their theory.
Right.
So let's go for a transaction and see if it works.
That's right.
We're not showing you whose account it is, just as we've been careful not to show any potential fraudster enough that they could carry out this attack. So now we just check to see that you've actually managed to pick it up, yeah?
Yep.
So the researchers have read off the name of the cardholder, their account number and their PIN.
The attacks that we've shown have demonstrated that it's easy to get the PIN as well as the card data out of the chip and PIN terminal. And this means that simply holding your hand over the terminal is no good. In other words, the customer cannot defend himself or herself, no matter how astute and careful they are. Therefore, surely the banks must take responsibility.
By showing that chip and PIN terminals can be easily compromised, the Cambridge team should now have made it harder for banks to blame the customer. There's now enough doubt about chip and PIN for the onus to be on the banks themselves to come up with the evidence that it was the customer and not the security of their chip and PIN system that was at fault.
Well, with us now is Sandra Quinn of APAX, which is the trade body representing the card issuers and users. How many chip and PIN machines are there in Britain?
Over 1 million. We have a lot of PIN entry devices, and the important thing to stress from this piece is that we're not talking about a break of the chip and PIN security overall.
Well, I think, according to that, we certainly are. How many of these Ingenico machines are there?
There's a large amount, but I think the important thing to stress is exactly what the Cambridge team themselves have said. This is a difficult fraud to do and to replicate in a large scale.
I never said
They did it by acquiring stuff on eBay.
Absolutely, and you can do this fraud. What we're very careful about saying is we don't deny that this fraud can happen, but as we currently stand, there are more economically viable ways of fraud being undertaken by fraudsters, and that's what our real concern is at the moment.
You have known that this system is vulnerable for a length of time you're not prepared to disclose.
Well, let's clarify. The system is not vulnerable. Chip and PIN is extremely
we've just
secure.
seen it's vulnerable.
It's not 100% guarantee against fraud.
So it is vulnerable?
No, there is no guarantee, 100% a guarantee against fraud.
So it's vulnerable, by definition. If there's no 100% guarantee, it's vulnerable.
All fraud, all systems have an inherent level of risk.
Sure.
And what we have done is look at the risks there, undertake a risk assessment and make sure that we protect our customers as much as possible.
And you would, why not?
Our cards are secure.
In that case, why have you introduced the new security devices?
Because one of the things that you have with chip and PIN is a layer of protection that you can build upon. So as soon as you see a threat, you can continue to build upon that protection with new and additional protection. And that's what we've done with chip and PIN. That's why this new card protection standard has come in this year. And that's why all the assessments that we do about terminals continually moves and is upgraded.
So despite the fact that new cards have enhanced security, the previous cards don't lack anything by not having it?
Well, I think the figures speak for themselves here. As the piece said, card fraud with chip and PIN has fallen.
In Britain?
In Britain.
The problem isn't in Britain, though, is it? And you know that.
Well, one of the reasons that we're making a very strong case to ask countries around the world to introduce chip and PIN to ensure that we're all operating on the same global standard so that we can make sure card holders are being protected properly.
Okay, so let's look into a little bit more detail about what was shown there. So here is the Ingenico PED again. That's what it looks like from the front, and this is what it looks like on the back. There's this extra compartment, and underneath there are slots to put SIM cards in order to extend the functionality of the device. And this compartment is normally not seen by the customer. There's a seal across it, but nobody looks at the seal. And also, there are these slots, and there's mounting holes that make sure the SIM slots don't move around too much, and these mounting holes go all the way through the tamper mesh. So it's possible for someone to put a paperclip through, as is shown here, hook on to the I/O line, the input-output channel, and then record the pin as it's going across and record the magstripe details. And even better, not only can we get this information, but we've got this hole in the case that the customer can't look at, so we can put a little device in here which records all the details and then sends it out over USB. The Dione PED isn't very much better. You do have to drill through the case, but because you don't have to open the case, it doesn't even attempt to trigger the tamper resistance measures. And then you have a wire that comes off here, and we built a FPGA board which does the translation between the ISO 7816 smart card standard and a serial port and logs all the information. It then dumps it out to a PC, and you can see on the right-hand side is a copy of the ATR, the answer to reset, the first bit of information that's sent between the card and the pin entry device. We've also got a miniaturized version of this device, which is just about big enough to fit inside the slot of the Ingenico terminal, and also it'd be not very hard to make it much, much smaller, so it would almost not be noticed. When the bank said that there are easier things for the fraudsters to do, what they were probably referring to is that there was an attack on the Trintec series of terminals in Shell garages in 2005. And this was used to, again, extract the magstripe details and the pin. But what we've now heard about as happening even before this programme was published on television, that fraudsters were doing exactly what we were warning was possible. And the total sum of money is very hard to estimate, but one fraudster was accused of collecting enough details to commit £16 million worth of fraud. So this type of problem is costing a significant sum of money. But that's not the only type of fraud that's possible. Much simpler thing to do is called a double swipe attack. Although there is a copy of the magstripe details on the chip, if you actually want to get the guaranteed copy of it, then you read the magstripe directly. And this is a screenshot from a video where a fraudster was working for a supermarket, and what he did was took your card off you, as many stops are now doing, swipe it through the normal chip and pin reader, and then swipe it through a second one that he had hidden. This then gets a copy of the magstripe. Then, either using a camera or just by watching, he can look at the pin that the customer enters, and then use this for the standard attacks. Another more sophisticated attack is the relay attack. This was presented at the previous CCC, but to give a reminder for those of you who were there and also those who weren't there, I'll very briefly describe how this works. So here, Alice, who is the honest card holder, wants to, say, buy a meal in a restaurant. But at the same time, there's someone, Dave, who is working in a diamond shop, and he's offering jewellery for sale. So the fraudster wants the jewels, and Alice wants the meal. So here's how you can set this attack up. So Alice puts her card into the chip and pin terminal in the restaurant, but the waiter is working for the crooks. So this isn't a real chip and pin terminal, it's just connected to a laptop. The laptop then sends the details to a second laptop, which is connected to a fake card held by Carol, another person working for the fraudsters. And Carol puts this card into the diamond store shop. So when Dave's terminal challenges Carol's card to say, "Are you a real card?" Carol just sends all the information back to Bob's terminal and to Alice's card, and then Alice's card sends the response back through this chain all the way back to Dave. So with this technique, it seems as if, from Dave's perspective, that Alice is buying jewels. Alice only sees the $20 pop up on her chip and pin terminal, because that can display whatever she wants. But when she gets her bill through, she'll find out that apparently she was in Dave's jewellery store and she just spent $2,000 on a fancy diamond ring. So I've talked about 3 issues in chip and pin. There are many, many more. And if this just affected the banks, then that would be more or less their own business. If they were willing to refund the cost of fraud because they don't want to roll out a possibly more expensive, more secure system, then that's up to them. The problem is that often the customer has to pay the cost of fraud. So this is a copy or some snippets from a letter, also available online, that is sent from the Financial Ombudsman Service to a customer who's been the victim of a phantom withdrawal, explaining why he shouldn't get his money back. So the first thing they say is that the firm has provided an audit trail of the transactions disputed by you. This shows the location and times of the transactions and evidences that the card used was chip read. Now, what does chip read actually mean here? Does it mean that the card details are read from the chip? Does it mean that the certificate was verified correctly? Does it mean that the transaction was authorised? Nobody really knows. And this particular customer had read some of the reports from Cambridge, so was a bit worried about the security of chip and pin, and in his letter he questioned the security of chip and pin. So what the Financial Ombudsman Service said, that although you question the firm's security system, I consider that the audit trail provided is in a format utilised by several major banks and therefore can be relied upon. So this would be like concluding that a document is in XML, and hence it's true. In practice, the documents aren't in XML, they're in EBCDIC, based on a format that originated from IBM mainframes and originally formatted for punch cards. But it looks about the same as the previous ones that we've seen, hence the customer is liable. So the customer wasn't really happy about this, so he asked for these logs and for some more information. And what the response was is, although you have requested this information from the firm yourself, and I consider it not obliged to provide it to you, I conclude that this will not make any difference because the service has already reviewed this information. So he doesn't have the information, he's being judged effectively in a secret court, and he can't pass this information on to anyone who is willing to give it any more scrutiny. Then they go on to say that chip and pin is secure. As we've already advised you, since the advent of chip and pin, this service is not aware of any incidents where a card with a chip has been successfully cloned by fraudsters so that it could be used for them successfully in a cash machine. Now, this statement is just false. They don't say that they used it in a chip and pin transaction. They say it's a chip card. I have cloned 2 cards, which are chip and pin cards, with the permission of the cardholder, I might add, and then used this in a UK ATM. But despite all that, the Ombudsman isn't going to give his money back. My conclusion is therefore that likely that the original card was used to carry out the transaction's disputed value. So that case is currently at court, but it's fairly typical of the response that people get, firstly from the banks and secondly from the Financial Ombudsman Service. And it's very hard to take this further. One of the points that John Gilmore raised in the keynote is that the US justice system makes it comparatively easy for someone to sue someone else. And this has many downsides, but it also has the upside that someone from the US was a victim of a phantom withdrawal. She took the banks to court, and the court ruled that because she was not able to inspect the bank systems, it would have been unreasonable to expect her to prove her own innocence, and hence the burden should be on the banks to prove to the courts that the customer actually made the transaction. And in most cases, US customers do get their money back. In the UK, the situation is very different. In the UK, if you sue a bank and you lose, you pay the bank's legal fees, which will often be in the hundreds of thousands of pounds, and they'll probably take your house off you. So it is extremely difficult to sue banks in the UK. Germany is somewhere in between, where there is a cap on the damages that can be awarded, but it still is very expensive to take on a bank over one of these disputed transactions. So I talked about a number of failures, but now let's talk a little bit about why these sort of things have gone wrong. There's a number of issues. One is that the PIN is not encrypted as it's sent between the PIN entry device and the card. This is a feature of the UK system, although other countries are very similar. And that's because it costs a little bit more money to put public key cryptography onto the smart card so that it can decrypt the PIN if it's sent in encrypted form. But that's not the only issue. There's also the problem that the circuit board, despite having a tamper mesh, had holes in it that someone can poke a paperclip through and hook onto the I/O line. It might seem a little bit stupid in retrospect that someone's built a system like that, but the engineers who are doing these systems have an extraordinary challenge. There are over 3,000 pages in the specification, and they have to make a device that complies with every one of these and still is cheap and reliable and looks good and all the other constraints that engineers have to do. And these security requirements can't be met by any one module of the chip and pin device. It has to be met as a system property of the whole. So it's probably infeasible, in my opinion, to build a device which protects this line between the smart card and the pin entry device, because it has to be exposed to the rest of the world, because someone has to put the smart card there. There's also the issue of economic incentives. The banks certify the devices that the shops can use, and the shops get to select what device from a limited list they can use. But the customer doesn't really get any decision in what type of pin entry devices they have to use in the end. And we can see this effect in the design of the security. The pin entry devices seem to do a reasonable job of protecting the bank secrets, but it doesn't protect the PIN, the customer's identifying number. And also all these devices were certified by either the Visa or Common Criteria specifications. There's a clear violation of the spec. It was meant to cost $25,000. In fact, it cost of a paperclip and a few $100s worth of electronics. And obviously there has been a failure at some stage in this certification. So in order to fix these issues, we need improvements at a number of levels. The PED design could be improved. There could be holes removed from the circuit board, but this is, as I described, an inherently difficult problem to solve. Because there is this exposed contact to the whole world, it's effectively infeasible to protect the information that's being sent across that. So instead, one option is card configuration changes. The card could be configured to support encrypted PIN, and it could also be changed so that there is no longer a verbatim copy of the magstripe stored on the chip. And this feature is called ICVV, which was briefly described in the Newsnight video I showed. What APAC's announced in that program is the ICVV, this new feature where they don't store the full magstripe on the chip, was mandatory as of January 2008. What Jeremy Paxman asked is, now there are more secure cards being issued in January 2008, shouldn't customers ask for new cards? And Sandra Quinn replied that because the old cards the old cards were just as secure, although there's more security devices on the new types of cards. But in fact, it doesn't make very much difference. I did ask for a new card from my bank, and they sent me one in February 2008, and it still had a full copy of the magstripe on the chip. So even though something was publicly announced as being mandatory, it's still not being applied. And this is common throughout many parts of the UK banking industry. Often things are mandated and then not implemented, but sometimes the mandate is relied upon when a decision is made about whether a customer is liable, and there seems to be nobody, at least nobody in the public community, who's testing the banking system to see whether they really implement all the security features that they're supposed to. There's also the issue of who's liable for frauds. The UK has something called the Banking Code, which is a voluntary code of practice which states that the bank must prove to the customer, in case of any disputed withdrawals, that the customer is liable for this and they have to pay. And that's good on paper. That's what it should look like. But unfortunately, the banks get to choose what evidence they store. And the banks don't have to convince a third party that the customer is liable. They have to convince themselves. And the levels of proof that they require for convincing themselves are fairly low. And because they're able to take this position, there's very little incentive for them to roll out new security measures. Now, this problem has been pointed out by the UK House of Lords. There was an investigation on personal internet security where this question was asked to the banks. They were told that the banking code said that they're liable and they have to prove that the customer made a transaction. So then shouldn't this be enshrined in law rather than being a voluntary code of practice? And the bank said no. So I mentioned that all these devices were certified. The Ingenico was certified under common criteria, and the Dione was certified under the Visa standards. So the way that common criteria work is that there's a certification body for the country appointed by the government which looks after implementation of common criteria in the country. In the UK, it's called CESG. They're also known as GCHQ. They're the same people who spy on people. In the US, it's a combination of the NSA and NIST, the National Institutes for Standards and Technology, I think. So because this was a UK distributed device, we asked CESG about this device and why it still passed certification even though it was clearly flawed. And they replied that they didn't really know, because this was not a common criteria certified device, it was evaluated. And there's a bit of a subtlety here that certified means that there is a public report that's produced on how the device performs, and this report is then sent from an independent testing lab to the certifying body for the country, CSG for example, and they say that this is a good device and it can be certified. What actually happened was that Apex went to one of these testing labs and, the manufacturer of the device chose a testing lab. The testing lab produced a report, it got sent to Apex, and then Apex then said that this looked good, and they were then happy to evaluate it. But they're not in any position to certify something. So this is a bit of a subtlety. It's a subtlety that's lost even to the common criteria board themselves, because the list of certified devices is on a web page entitled List of Evaluated Devices. So there is an issue here that consumers are being told that these devices are being certified to an international standard, and they're not. They're effectively being self-certified by the banking industry themselves. We also asked Visa, because they certified both of the devices that we looked at as being secure, and they didn't respond to any of our questions. There is a copy of all the letters that we got on our webpage. The Apex one goes into quite a lot of detail and is worth reading. So there is clearly a failure here in the common criteria certification. So we asked CSG and Apex what they were going to do. CSG said that we need to discuss this with Apex, and Apex said that the responsibility for this is CSG. And as far as we can tell, these devices are still certified and still listed on the Apex website as being evaluated under common criteria and are still in very wide use. There's also the issue of secrecy in certifications. We asked Apex for a copy of the evaluation report that was produced by one of these labs, and so we could look at it and see what went wrong. Did they not do the tests we did? Did they not consider the possibility that someone could go in through one of these holes? Did they consider that this was an acceptable risk? In common criteria, you can declare that something is certified even if it doesn't meet all the requirements of the certification, but you have to write that you've done this in the report. And what Apex said is that no, we can't have the report, and that they are not aware of any widely recognised or credible evaluation methodology, process, and security or otherwise, which makes evaluation reports publicly available. And again, they say that secrecy is necessary for security, because if we say how the devices work, then it will reduce the effectiveness of these controls. Now, clearly, it hasn't worked. These devices are fairly easy to break, and they are being broken by fraudsters. And I think instead, a more hostile evaluation, rather than being done by an evaluation lab that's contracted by the manufacturer of the device, is more likely to find some flaws. What CESG said was the exact opposite. They said that the publishing of evaluation reports is mandatory. So again, we have this contradiction between APAX and CESG, and it's very hard to see how to resolve this sort of issue. Okay. So, in summary, there's a number of problems with chip and pin, but they're due to a combination of certification, regulation, and incentives. The protocol designers managed to save some costs by allowing the pin to be sent in the clear between the card, between the PED and the card. But in doing so, they imposed an unrealistic cost on the designers of the pin entry device and requiring it to protect this I/O line. And that again left customers at the risk of quite significant levels of fraud, and often fraud that they cannot be refunded by. I don't think any of the people who designed this were stupid. They were just put under unrealistic expectations. They had a 3,000-page spec to work from, and also a spec that is under fairly rapid change. Maybe when they first looked at it, encrypted PIN was mandatory, but then later on it changed, and they had to evolve their device to take into account this new environment and new set of constraints, and in the end created a device that was not secure. And I think looking at the design of the system overall from the perspective of incentives is a useful approach. We've seen that the person who controls the design of the system, i.e. the banks, has their interests comparatively protected, but the customer, who has almost no control, is left very vulnerable. And I think the lessons from this are not just applicable to banking security. We've got the same set of problems with voting machines. Voting machines are certified and found by various organisations to be completely secure. There's a lot of resistance from manufacturers for any sort of analysis into these devices. So I think the issues that raised here are certainly applicable to voting machines, and probably also to many other areas of research too. So that's all from my talk, but there's lots more information on my website. The address is down there. There's videos, an extended version of the paper where we go into a lot more detail, and also the letters from the vendors. Yeah, question?
You said earlier that you had cloned 2 cards. Presumably you had just put created a magnetic stripe with the magnetic stripe data from the chip.
Yep.
Are you aware of anybody cloning the actual whole card?
So there has been fraud in France where people have cloned the chip as well. And the reason they're able to do this, if I just go back to the protocol diagram, is that there's a static digital signature over all the card details. This doesn't assure you that the thing you have is the right card. It assures you a right card actually exists. So if you make a clone of this, then you get a copy of both the chip and the mag stripe. This won't work for all types of transaction, because the last stage here is symmetric cryptography, and it, at least in principle, can be detected that a clone exists. But in some countries like France, chip and pin terminals regularly do not contact the bank in real time, and so you can do a clone of a chip like this. Yep.
Yes. I have one question. Yes. So in France, on the carte bancaire official website, it says if there is a dispute on the amount of the transaction, which you can modify in, like in the relay attack, okay, go to the shop and complain, whatever. It's your problem. This is the official position.
Okay.
What is the situation in the UK? And will the police investigate this kind of problem?
So there's two problems in the UK. On paper, it looks good. The customer should go to their bank, and if the bank can't prove that they did the transaction, the customer should get their money back. In practice, the situation is not so good, because if you're part of a big set of frauds, if you're just one of 100, you'll probably get your money back. If you're one of a smaller number of frauds, then the bank might not believe you. They might think that you're trying to defraud them. The second problem you mentioned about the police. It's no longer possible for UK cardholders to report fraud to the police. They have to report to the bank, and then the bank can then decide what they report to the police. And unsurprisingly, the amount of reported bank fraud has dropped dramatically. And this makes the banks happy because no one's looking at it, and it makes the police happy because the stats have gone down.
But the specific question raised was the amount of the transaction. Is there a possibility to actually reliably know the amount of the transaction, for example? And
this is signed as part of the audit logs, but the banks will, in general, not let the customer see a copy of the audit logs. It's not clear they have a copy.
They refuse, yes.
They refuse, yeah.
I've heard reports about PEDs being modified by the manufacturer, so they actually contain a Trojan or something that does that. Is that something that you've looked into as well, or is the manufacturing process certified in any way? Or
it's not something I've looked to personally, but I have seen the reports and they do seem very plausible. These devices are all manufactured in China. It would be fairly easy to add an extra module inside them that hooks onto this I/O line and then records all the details. What the reports were is that not only would it record the details, it would use a GSM modem to send it off to Pakistan and then do fraudulent transactions over there.
So the only way to really solve this is to have end-to-end, the card communicates directly to the bank computer and do something that basically just tunnel the communication between there.
I believe in that case, the frauds were committed using magstripe fallback. So that is another set of flaws. That's an effect of encoding a copy of the chip, of magstripe, on the chip. Hopefully that will be corrected. Obviously they're not on the time schedule that is disclosed, but if that is being corrected, then it should stop this type of fraud. But there are other designs of chip and pin terminals which do read the magstripe as well. And if the fraudster tampers with one of these, then they've got a copy of the magstripe. So in that case, all you could do is turn off magstripe fallback.
I was just thinking, how would you design a system that should be totally secure if you were to design one?
I think in my world, the first thing I'd do is make the banks liable for fraud and then leave it up to them to design the system to be secure enough. Because there are very expensive modifications you could make to these to make them more secure, but maybe the losses of fraud don't justify it. If the banks are paying for the costs, that's a fine decision for them to make. But if they decide what to do and the customer pays, then it's not a fair situation.
Hi. Do you think it is possible to use this study as a proof to get your money back in case of a fraud?
People have tried doing this, but remember I said that all the banking code says is the bank has to convince themselves that the customer does it, and they don't believe me. Maybe if this goes to court, it will be a different story. We'll have to wait and see.
Are there any questions from the back?
Something else maybe. Do you have an idea about the mobile card readers, how the data are transmitted back to the main terminal somehow? Is it?
Yeah, I haven't looked at it.
Okay.
The specifications say that it must be encrypted. It doesn't say how good it has to be encrypted.
Web is also encrypted?
Someone with a protocol analyzer should look.
Mm-hmm. Thank you.
Hi, and you mentioned in the last stage, some of the PED device is not connecting to the banking in the real-time transaction
Yes.
money. So how did you know this device actually is not transaction in the real time? Is any document information about from a banking website or is device? I was trying to find out. If I say I go back to China, right, and I find there's a device, PED device, so how do I know this device is not transaction connecting to the banking in real time? Is any words?
No, there's no way for the customer to tell that one of these PIN entry devices is legitimate. To do a demonstration of this, we took an example from the voting machine campaigners. They made their voting machine play chess, so we made our PIN entry device play Tetris.
So even the shopper, the retailer, the vendor themselves, they can't tell. So if I'm the owner of a shop, and I own this PED device, I can't even tell this transaction is real time or.
If you're watching it, you can see whether it connects to the bank using a modem.
Oh, okay.
So that's one way to do it. If the chip and pin terminal has been tampered with, then there's no way to tell because it will just pretend to dial up the modem and is actually not. So in some cases, fraudsters have been replacing chip and pin terminals with other ones and then using this to either record details or do other types of fraud.
Thanks.
Just before we take one last question, there's been a small change to the programme. About 4 o'clock, there'll be a talk by Boris Denev on the individuality of active and passive devices, instead of either the blank spot or a token RFID. So is there one last question from the audience?
So if this connection is not like real time, how big is the delay between the PIN pad saying, okay, your money is being booked and the actual action taking place?
Is that for offline terminal when it's
some generic store, I guess, something like this.
So there are two ways that this is normally done. One is that the phone line is considered as expensive, so it will not do a dial-up connection for cheap transactions, but when it goes online for an expensive transaction, it will also send all the previous details. The other case are examples where there's no connectivity at all, for example, a chip and pin terminal on an airplane, and then it does the actual real-time device when you plug it in.
So what would be if I pay with my card and then do anything to destroy the terminal before it actually has a chance to connect back to the bank, which is, as there are all these meshes, seems to be quite easy, like pushing a needle somewhere in or something like this.
Yeah, then
so
you won't have to pay.
Shopping for free.
Yes.
Well,
hopefully
fine.
the merchants will be sensitive towards that, but at the moment I don't think they do any particular protection.
Thanks a lot. And thanks again to Stephen for coming and giving this fantastic talk.